Hi everyone. So today I will be starting with the topic of nuclear physics. That's chapter 26. Um, we will be looking at Einstein's mass energy equation and what it means, how energy is released or absorbed in simple nuclear reactions, also how to calculate that using Einstein's mass energy equation. We'll also look at creation and annihilation of particle and antiparticle pairs and how to calculate the energies released in those reactions. We'll introduce some new terms such as mass defect, binding energy per nucleon, and what that could mean. You will also need to be aware of the binding energy per nucleon against a nucleon number curve, which will specify whether there will be a fusion or fission reaction depending on what we see there, and how to calculate the binding energy of nuclei using the equation that you see there. So I will start first with Einstein's mass energy equation, then we'll proceed on to how to do the calculations of each part. So you must have all seen this equation everywhere. That this is one of the most famous equations, but not many people really understand what it means, but you will. This idea was proposed basically by Einstein in 1905. It can be seen as two ways. So when I say what do we see from this equation, well, we can see that energy is mass, and mass can also be seen as energy, so it's interchangeable. So in one way of seeing that mass is a form of energy, that can be seen in annihilation calculations, and then that energy has mass. We'll see that in the reactions later on. So E stands for energy in this case, is always measured in joules. M is for the mass, which is measured in kilograms, and C is the speed of light in vacuum. So that's a constant that you already know. So in other words, it is directly proportional to mass. So energy is mass and mass is energy, depending on which way we see it. Now, when we say energy has mass, I want you to consider an object that's at rest. So usually we take objects' mass at rest to be called the rest mass, meaning that they're not moving. Now if they start moving, so let's say, for example, a ball, so while it's not moving and we measure its mass, that's called its rest mass. But once it starts moving, it gains kinetic energy. Therefore, it will have more mass while it's moving. So that's why we can separate that from rest mass. So you will see the word rest mass a lot in this topic in terms of particles. We're not going to be talking about huge objects and stuff, but yeah. Now this is a nice example to just have a quick look at how tiny of an effect moving has on our gaining kinetic energy has on the person's mass, and we will calculate that as well. So if we consider a person that while he's at rest or she is at rest, they have 70 kilograms of mass in a car. Now, if the car starts traveling at 15 meters per second, that means that the person will also gain kinetic energy while the car is moving. We can calculate that increase in kinetic energy using this equation here. So that's the increase in kinetic energy, and hence this is the increase in mass. C squared, once again, is the speed of light squared, so that does not get affected. So how can I calculate the mass of the person gained? Well, I already know that the car is traveling at this speed, so I can find the kinetic energy of the car and equate it to Einstein's equation. So I can be able to calculate that mass, the increase in mass or change in mass. In this case, it's increasing. So the change in the energy will be the change in the kinetic energy that the person has gained. So that will be a half mv squared, where here is the mass of the person. V is the speed that the person's traveling within the car. And then you have the change in mass divided by c squared, which you'll be calculating. So if you rearrange for delta m, you will have a half mv squared over c squared. Then once you place all your values in, you should get a very, very tiny value of about 8.8 times 10 to the minus 14. So that's roughly a value of 10 to the minus 13 kilograms. Now, if you go on a scale cannot read up to that precision. So you can see that for humans or big objects that are traveling at slower speeds, there is not much change. Now, all these changes when it comes to particles, because they have smaller masses and faster speeds. So this equation basically shows a big difference between the rest mass and the mass gained by a particle moving, in terms of the fact that it will have obviously much faster speed, hence much higher kinetic energy, and that will affect the change in mass more. So how does that apply in radioactive decays? When you have a parent nucleus that emits either an alpha or a beta particle, it has to follow what we call a mass energy conservation law. Since we have introduced now Einstein's equation, it's very important to realize that mass energy have to be conserved as a total. So we know that during a decay, energy is being released. So that means that there must be a decrease in the mass that's equivalent to the energy released. I'll give you an example. So let's say you have a particle, a nucleus that's unstable, and it breaks down by emitting, say, an alpha particle and a daughter nucleus. Now, obviously, the alpha particle and the daughter nucleus will move away from each other. They will have kinetic energy. So just by talking about conservation of energy, we won't be able to fully understand what's taking place. So we have to use the terms of conservation of mass energy. So the total amount of mass and energy in a system has to be conserved. So since in this case energy has been released in this decay, there must also be an accompanying decrease in mass to the energy being released. So in other words, the mass of the daughter and alpha particle will be less than the mass of the parent and parent nucleus. So the combined mass, so this is the daughter nucleus. Since they have kinetic energy, then they have less mass. So we're conserving the energy here. So their mass is less than the parent nucleus, since energy has been released in the form of kinetic energy. And then this is your parent nucleus. So this is the perfect question, example question, to have a look at what exactly is going on, or what I meant in the previous slide. So we have the decay of carbon-14 nucleus, that is represented by the decay equation below. It says the carbon-14 nucleus is initially at rest, and it says use table 1, so the table that's presented next to the question, to calculate the total kinetic energy released by the decay of a single carbon-14 nucleus. So we know here that we need to apply the energy mass conservation. So in other words, I need to make sure that I calculate the change in energy, which is equal to the change in the mass of the parent to the daughter nucleus as well. So the initial mass, so we start first with the change in mass. We can do the final mass of the combined nitrogen and electron that were given out, minus the initial mass. So that will be, so these are given to you as multiples of 10 to the minus 26, these values. So the final mass, which is the combination of the two, will be 2.325223 plus this times 10 to the minus 27. And then you subtract the initial mass, which is 2.32539114 times 10 to the minus 26. Sorry, that was minus 26. I put the wrong number there. Now, when you get the change, it will be minus 2.8 times 10 to the minus 31. So in this case, you notice that there is a minus sign there at the beginning. That means that energy has been released in this process, since the mass, the final mass is less than the initial mass. That means the energy has been released. And now I can use the equation here fully and just simply calculate the energy, the change in kinetic energy that has been released in this reaction, decay. We don't even need the negative sign, to be fair. And 3 times 10 to the 8 squared. That should give you an answer of 2.52 times 10 to the minus 14 joules. So we are taking it once again. We are considering the mass, the final mass and the mass before. We get the change in that, so we can be able to find the total kinetic energy released during this decay process. And the fact that we got a negative sign means that the energy is being released and not absorbed to cause the reaction, to cause the decay. Now, this also fits in really nicely with what we learned in chapter 24 in particle physics. We introduced particles and antiparticles, and we said when they meet with each other, they annihilate each other, they completely destroy each other. But obviously, we need to apply the mass energy conservation here as well, because nothing can be created or destroyed. So what happens instead, their mass is fully transformed into energy in the form of two identical photons. We already know that the positron and the electrons have the same mass. So here we have the mass of one electron and the mass of the positron. So I'll just use the connotation for annotation. So remember, this is an electron, this is a positron. The line at the top shows you that it's an antiparticle. And in this way, we can figure out how to calculate the minimum energy released. And when we say minimum, why is that the minimum energy? Because we will be using the rest mass of the electron and the positron. We also know that the photons will have kinetic energy too, so there might be more energy released in the whole process. But we are using the rest mass. We are assuming that the electrons are actually not moving. So here, if we have, again, our equation, if I want to know how much energy is being released in the annihilation of the electron and the positron, I know there is a specific change of mass. In this case, it's the mass of the electron plus the mass of the positron, which is simply 2me c squared. And once you place the numbers in, so I will use the values given to me here, 9.11 times 10 to the minus 31. And you will get an answer of 1.61398 times 10 to the minus 13 joules. Now, this is the energy released when the electron and positron annihilate each other. However, since there are two identical photons emitted, that means that's the energy shared between two photons. So if you want to know the energy of one photon, you just simply divide it by two because they're identical. So you just divide that by two to find the energy of one photon, which is about 8 times 10 to the minus 14 joules. You already are aware that we tend to use electron volts usually for such small amounts of energy, especially when it comes to particle physics. So for you to get from joules to electron volts, remember you just simply divide it by 1.6 times 10 to the minus 19. This gives you the energy of a photon as 5.1 times 10 to the 5 electron volts. I can simplify this further, so I can divide it by 10, multiply that by 10 to the 6, 0.51 times 10 to the 6 electron volts. We know that's mega, so there's the answer. Okay, so just like this annihilation process, there's also pair production process, meaning that you can have a single photon that breaks down into a particle and its corresponding antiparticle. So in pair production, a photon will vanish and all that energy that the photon had will create a particle and an antiparticle. We can, in any way or form, energy can also create matter if it's under the right conditions. So at the beginning of our universe, when it was really, really hot, a lot of particle and antiparticle pairs were being formed and also destroyed at the same time until the temperature of the universe cooled down, where more and more particles were formed. This method is also used in particle accelerators, where they usually use very energetic protons to smash them together. Then their kinetic energy gets transformed into other matters, and so on and so forth. But yeah, it needs very specific conditions. Now, you should be able to also calculate the energy of a photon that can create an electron-positron pair. We already calculated in the previous part that each photon to create a particle and an antiparticle, each photon in the annihilation process, so each photon gets 0.51 mega electron volts of minimum energy, because we're considering that the electrons have a rest mass and they're at rest. The electron and the positron, sorry. Now, if we have a single photon splitting into a particle and an antiparticle, it will need to have double that energy. And so it will be 2 times 0.51 mega electron volts. So for one photon to be able to be split into a positron and an electron, it will need to have minimum this much energy. So now diving a little bit deeper before we start introducing the next lesson, fission and fusion. We know that nucleons are bound together by the strong nuclear force. So you need to do work to separate them. You need to transfer energy to break them apart, all the nucleons in the nucleus. So basically, if you want to split the proton, the neutrons inside the nucleus, you'll need to provide energy to be able to separate them because they're bound by that strong nuclear force. So how would the mass, now that we know about the mass energy conservation compared to the mass of the individual nucleons, if we separate them? Well, the mass of the nucleus is actually less than the mass of the separated nucleons. So, since we need to provide energy to break it apart, that means that that extra energy is given to the nucleons individually once they're separated from the nucleus. And we're going to see this applied to some different situations as well, and the graph of why this actually happens. So before we get to that point, you need to learn a few key terms. One of them is the mass defect. This is simply defined, and you do need to know these definitions. It's defined as the difference between the mass of completely separated nucleons, meaning separated protons and neutrons of the nucleus, and the mass of the nucleus. So, in other words, it's a change in the mass, which is the mass of the nucleons separated, so the total mass of the nucleons separated minus the mass of the nucleus. That's the mass defect. Then if we look at binding energy, is the minimum energy needed to completely separate a nucleus from its constituent protons and neutrons. So we put this in terms of Einstein's equation, which is pretty much the same thing. Binding energy of a nucleus is equal to the mass defect times c squared. Now, even though this formula is not given to you in the formula booklet, it's just another way of seeing this equation. But in this case, we're clarifying what this mass defect is and this binding energy is. So you don't have to memorize it in that way, but you do definitely need to understand what binding energy and mass defect is, and why in fusion and fission reactions there's always a release of energy. Okay, so here I have an example question that we'll go through. Just to make you aware, I will be using the atomic mass unit for the protons and neutrons. I will also ignore the mass of the electron because it's not that significant. So to be able to calculate the binding energy in mega electron volts, so binding energy, remember, is the minimum energy that you need to completely separate the nucleus from it. Basically the energy that you will need to provide the nucleus to break it completely up to its neutrons and protons separated. Since we already said that we can use the equation binding energy is equal to the mass defect times c squared. Remember, the mass defect is just the difference between the mass of the completely separated nucleons and the mass of the nucleus. The question gives me the mass of the nucleus already. So here I know the mass of the nucleus, but I need to find out the mass of the total mass of the separated nucleons. And for me to do that, I just need to know how many protons and how many neutrons there are. So there are 92 protons, and you do 235 minus 92 for the number of neutrons. So there's 143 neutrons in the nucleus. So now I can calculate the total mass of the separated nucleons using these values here. So I have 92 protons, that's times 1.00728. By the way, the questions can give you their own values as well. So for the masses or units that they want you to calculate. So don't worry about having to remember anything besides the main concepts that they will all be given to you. And then I add the mass of the separated neutrons, which is a little bit heavier, as you can see from there. 667. Let me use the values that were given there, and basically all of that is times U, the atomic mass unit. So that roughly gives you a value like this. Now the Second step, so I calculate the total mass of the nucleons, so now I can calculate the mass defect. So basically I can take the difference between the total mass of the nucleons that are separated from the mass of the nucleus as a whole, and that will be 235.004393 minus, don't forget U, because U is very important to include in the calculation at the end. So you will get a change in mass. Remember, this is U, so I have to multiply. Oops. So I have to multiply my value by the value of U. Sorry, I don't know what happened there. Yep, there we are. So that will be 1.901494 times the atomic mass unit, which is 1.661 times 10 to the minus 27. And your mass defect comes out to be 3.16 times 10 to the minus 27 kilograms. So this is where I can calculate the binding energy now straight away. I just simply have to multiply this mass defect with the speed of light squared. So that will be binding energy is equal to that number times the speed squared, which gives us a value of 2.84 times 10 to the minus 10 joules. However, it did ask us to give the answer in mega electron volts again, so I need to divide my value by 1.6 times 10 to the minus 19, which will give me 1.779 to the 9 electron volts. So you can rewrite it as about 1780 mega electron volts. Now, you would expect that the binding energy of bigger nuclei to be much bigger, and that's because they involve more nucleons. However, we tend to the binding energy on its own doesn't tell you how easy it is to break up the nucleus. It doesn't tell you how stable the nucleus is. So in order for us to compare how easy it is to break up nuclei, it would be more sensible for us to use the average binding energy per nucleon of the nuclei that we're investigating. So, for example, the binding energy of uranium is much greater than the binding energy of deuterium, which is just a hydrogen isotope. However, the average binding energy per nucleon is actually used to compare how easy it is to break up the nucleus. The greater the binding energy per nucleon, the more tightly bound the nucleons are, and the nucleus is more stable. So I will show you. So for example, let me just pick uranium. So if I pick uranium-235, uranium's binding energy alone is about 1000, we just calculated it, mega electron volts, sorry. Now if I wanted to find its binding energy per nucleon, I just simply need to divide the total binding energy by the nucleon number, so the number of protons and neutrons total in the uranium. So that will be divided by 235, since it's the uranium-235. And that will give you 7.6 mega electron volt energy per nucleon. Now, if I look at, for example, deuterium, that's 2.1, that's deuterium. Now, the binding energy of deuterium is 2.2 mega electron volts, as expected, because obviously it only has a proton and a neutron, whereas uranium has 235 protons and neutrons. However, if I consider the binding energy of deuterium per nucleon, There's only 2 nucleons, so you divide that by 2 and it will be 1.1 mega electron volts. And this is very important when we start looking at fusion and fission. So in the next lesson, it will be incorporated a little bit more. This is a really important graph. You do need to be able to analyze it. You do need to be able to remember key features of it. But basically what it has is the binding energy per nucleon, so in mega electron volts each, obviously, and the nucleon number on this axis. So basically how many protons and neutrons they have in total in there. There's a few key features of the graph. So you can see that with nuclei, the highest, the most stable out of all of them is iron 56. It has the highest binding energy per nucleon, which makes it the most stable. So anything below a nucleon number of 56, you can notice that there's a general pattern where, let me just use a little, so you can see that the binding energy below this is increasing as the nucleon number increases. For nuclei that have greater nucleon number than iron, so from iron further down to uranium, you can see that the binding energy per nucleon decreases as the nucleon number increases. Like I mentioned already, iron 56 has the greatest binding energy per nucleon, which means it's the most stable isotope in nature. But you can also notice a few other little peaks before iron. So you can see that helium has a higher binding energy per nucleon compared to lithium. So that makes helium more stable than its neighbors, the ones before and after it. The same thing that you can notice as well for oxygen. And that's oxygen and that's carbon. So helium, carbon, and oxygen, all of them have a bit more stability than their immediate neighbors on either side. So they don't follow fully the pattern, but there are abnormalities to the pattern, and it's probably quite important in the way that we formed and how we survive on that. Now, we spoke already before about energy released in natural radioactive decay. We can use now this graph to show how in a spontaneous decay, the total binding energy of the parent nucleus, so for example, if you had uranium and it spontaneously decayed into something smaller, the binding energy of the parent nucleus is always less than the daughter nuclei that are within this line. So that means that the difference in the energy released is in the decay is the kinetic energy, basically. In a fusion process, when you have two low nucleon number nuclei combining together to produce a higher nucleon number nucleus, you can also see that the smaller elements or isotopes that combine have lower binding energy per nucleon compared to something bigger that they would have formed. So once again, the newly formed nucleus will have greater binding energy than the initial nuclei, so energy will be released. So fusion is something that happens in the sun and in the stars, like our sun. So that's how they release their energy, because they have elements that have lower binding energies and they form into something that has greater binding energy. So energy is being released in the process. Now, in fission processes where you have a huge element splitting into smaller elements, smaller nuclei, energy is being released because the two nuclei produced will have binding energy. So if they say, for example, one here was released, it will have bigger energy than the uranium, and therefore energy is being released in this process too. So that's why energy gets released in both fission and fusion. There is also a nice video that I could add the link if you want me to, that explains it in a different way than this, but this is the scientific way of explaining it. Hope you found this easy, and if you do have any questions, do let me know.